Good morning, everyone. Welcome to Exoplanet Biosignatures for the 2020s and beyond. I'm pleased to be representing some of our co-conveners and co-chairs here as we welcome a number of lovely talks this morning that are going to be both in person and virtual. Eddie is in the audience. For those who are present, he's going to give you 2 minutes, and then he'll stand up at 13 to know that we're transitioning to the next talk. But first, I would like to welcome Camille Butkus to the stand to talk about graphene hydrogenation. So thank you.
Okay, hello everyone. So we'll be talking about biosignatures today, and I'll be discussing space weathering as a source of abiotic methane on exoplanets. And so a little bit of the motivation for this research is that the James Webb Space Telescope launched this year, and it'll be looking for these gaseous biosignatures on exoplanets. So among those will be oxygen and methane, and we're particularly interested in methane because it's a relatively well-known biosignature. And so what we want to look at is if we're going to detect methane in an atmosphere, is it actually coming from life or not? So that's the motivation behind this research. So what makes methane a relatively robust biosignature is its short photochemical lifetime. So here we just see how it easily breaks apart by radiation, and so it doesn't last very long in an atmosphere. And how we get it to stay in an atmosphere is we have these really large fluxes, and these are mostly produced by methanogenic microbes that we have here on Earth that sustain the methane in our atmosphere. But we also know that planetary chemistry is much more diverse than what we just have on Earth. So Earth is relatively an oxidized mantle redox state that we have here on the x-axis. And so in this case, we might have volcanoes, and they'll produce carbon dioxide and maybe a little bit of methane, but that should be oxidized fairly quickly. So in the case of a planet where we have an oxidized mantle redox state, if we're still seeing large quantities of methane in the atmosphere, we can presume that it's coming from life because it needs to have such a large flux to sustain it. So this would be a biosignature. Now, on the opposite end of the spectrum, if we have a relatively reduced mantle redox state, these volcanoes might be spewing out methane that's not going to be oxidized, so this would be a false biosignature where we would detect methane, but it's not actually coming from life. So we're also going to look at altering the abundance of carbon in the crust. So we'll put that on the y-axis with low on the bottom and high on the top. And in this bottom left corner, it's relatively well known that abundant abiotic methane is unlikely. These are kind of the conditions for Earth. So when we see a lot of methane in the atmosphere, it's likely a biosignature. And so the other three quadrants we have here are less understood, and it gives us a lot of opportunity to ask, how might methane be produced without life here? So today we're going to focus on the top right corner, where we have a reduced mantle redox state and a relatively high abundance of carbon in the crust. And so we'll call this space weathering for today, where we have a lot of graphite in the crust, a reduced mantle redox state, so lots of hydrogen, and this is what we presume will give us methane as a potential false biosignature because there's no life involved. So we started this research by looking at past studies that were done, and we found this experimental analog called a tokamak. And so inside this tokamak, all of these tiles that line the inside are made of graphite. And inside, hydrogen ions spin around in like this torus donut shape under high pressures and relatively high temperatures. And they interact with the graphite tiles, and they erode them, and they produce methane. So this is a problem for the engineers that are creating these devices because they don't want the graphite tiles to erode. But it's good for us because we know that this reaction does occur and produces methane abiotically. So if we translate this to the context of space, Blewett actually proposes that this reaction also occurs on Mercury. So solar winds supply protons for space weathering on Mercury. And just a quote to kind of explain what Blewett's getting at here is, heating and mixing of graphite with solar wind saturated material, which are these protons, may also lead to the production of methane and might initiate and sustain the growth of hollows. So what Blewett's getting at is that these protons are bombarding Mercury's surface, which has a lot of graphite, and through that interaction, they're producing methane abiotically, and as a result, they're forming these hollows, these shallow craters. And we'll also refer to this as ablation later on. So to go back to kind of the tokamak experiments where scientists were just bombarding graphite with protons, we can look at this interaction and the equations developed by Roth and Garcia Rosales to quantify how much methane we might expect to see. So they have this equation, they did a bunch of experiments and then made an equation to fit the results of methane yielded, and it's comprised of three terms: this physical, thermal, and surface erosion, with lots of equations that go into each part of this. But it's primarily focused on three parameters: ion energy, ion flux, and temperature. And so we can see that our experimental values from Roth and Garcia Rosales differ quite a bit from Mercury. So, we're going to run this equation, but we're assuming that it still holds true under slightly different ion energies, fluxes, and temperatures on the planet. Okay, so we'll go back to the slide real quick. We have three independent variables, and then our dependent variable is this y tote, which will be how much methane we're expecting to see from the reaction. So then that gets us to our graph here. And so we'll just look at the axes first, and then we'll focus on the big colorful thing in the middle. So on our y-axis is temperature, on our x-axis is energy, and on our z-axis is flux. And then, so those are our three independent variables. And then our dependent variable, how much methane or carbon atoms we might expect to see, is in a log scale on this color bar on the right. So then we can look at the colors, and we find that methane yields are highest at moderate temperatures, which is around this like 500 degrees Kelvin, which is moderate for Mercury, but it's obviously still very hot. These low energies, and the methane yield increases as we get higher flux or higher rate of delivery of the ions to Mercury's surface. So this just lets us see this very upper bound of how much methane we might suppose would come from this interaction on a planet like Mercury. So we can take that very upper bound just to constrain us and convert it to millimoles per meter squared per year of methane coming off of Mercury. And just, for context, we can compare it to a couple things. We can compare it to Mars. It's several orders of magnitude higher than the methane we see present in Mars' atmosphere, but much, much lower than Earth. But as we know, Earth has a lot of biotic methane, so high fluxes, which sustain the methane in the atmosphere. But we do know of two abiotic processes on Earth: serpentinization, which is a rock-water interaction that yields methane, and volcanic outgassing. And so the methane flux we see on Mercury is actually pretty similar to the amount we would suspect from serpentinization on Earth, which, it contributes, but it's a relatively low contributor. And it's a little larger than volcanic outgassing on Earth. So we can return to Blewett's paper to look at the formation of these hollows, and we find that space weathering of graphite to methane can account for a fraction of ablation, or this hollows formation. So again, taking that maximum methane yield to just constrain us, and converting it to meters of graphite over the entire lifetime of Mercury, we see that we would get maybe around 1 meter deep craters, while the mean depth of the hollows that Blewett found was 24 meters. So this interaction could be occurring, but it's not a super significant contributor. So this leads us to kind of sum up some implications for exoplanets that might be close to stars, because this is where we want to see if we'll find methane in an atmosphere. So we know that protons that reach a surface of a planet can react with graphite. And again, that's just this interaction of protons with graphite. They'll yield methane abiotically. However, we have to, consider, are these planets habitable? So atmospheres on magnetic fields on habitable planets might deflect the incoming proton flux. And additionally, the conditions for space weathering, which are hot and close to the star, kind of like we see in the image on the background of this slide too, are not habitable. So this interaction, wouldn't occur to give us a false positive biosignature in the presence of life also. It's kind of one or the other. So this leads us to roughly conclude that space weathering of graphite by these stellar protons is likely not a major source of abiotic methane on habitable planets. And with that, I'd like to thank Research Corporation for Science Advancement for funding this entire project, and my PI, Jennifer Glass, and the Glass Lab, and my collaborators at University of Chicago and UCLA.
So if we have any questions, it was so if we have any questions, please state your name and affiliation, and then you can ask questions. Thanks.
Goldman, NASA Goddard Space Flight Center. That was awesome. Really, really cool stuff. Have you thought about other biosignature gases that might also have similar weathering mechanisms for their production?
Wait, could you repeat that? Sorry.
Are there other biosignature gases beyond methane that might have their own weathering sources?
Yeah, so we only looked at methane, but I'm sure that the similar process could be, contribute to some other gas. Yeah, in the context of this, space weathering we refer to as like graphite hydrogenation, but space weathering can be a lot of different things. So I think it'd definitely be extrapolated to that.
Cool, thank you.
Hi, Elsa Ducrot from AbSciCon in Paris. I was really cool to see this. I'm wondering, have you tried to compute what would be the detectability for an exoplanet, for example, a really close exoplanet to its star, considering it has no magnetic field, etc., just see if it's detectable?
I can't hear the question.
Is the methane detectable for a planet that's really close in?
Oh, is it detectable? Okay. So, I don't really know the limits of what is detectable and not detectable, but what we found here is that it's a very, very low quantity. I don't know what James Webb Space Telescope can detect, though.
Okay.
Do we have any questions from So next up we have Michaela Lung, who's going to talk us about methyl bromide. So we should be seeing her slides, and you can take it away, Michaela.
Thanks, Sunny, and good morning, everyone. My name is Michaela Leung. I'm a PhD student at the University of California, Riverside, and I'll be talking to you today about my work on methyl bromide and specifically its application as a novel exoplanet biosignature candidate. I'd like to thank my advisor, Dr. Eddie Schwederman, and our collaborators, Drs. Nikki Pronto and Thomas Fauché, for their helpful contributions to this project. So methyl bromide is the first of a series of novel methylated biosignatures that we're investigating. And we're particularly interested in this group because they have a number of advantages. The first of which is that they have low false positive potential. So kind of in a planetary atmospheric context, there are very limited pathways to generating these gases abiotically. And we don't think that those processes could generate the same levels as these biological fluxes. So it's really unlikely to generate a false positive signal of these methylated gases. Additionally, methylated biosignatures are generated by a common metabolic process that is connected to local environmental detoxification, particularly by microbial species. And so we suspect that that may make it more likely, potentially, than other processes to arise on an exoplanet or under different biogeochemistry. And then finally, these methylated biosignatures already have 2 established members. So there's methyl chloride, which was first described by Segura et al. In 2005, and dimethyl sulfide, which was first described by Domagal Goldman et al. In 2011. And so those are kind of the first 2 members of this group of methylated biosignatures. So to further explore methyl bromide as a biosignature, we use a series of models, the first of which is the Atmos one-dimensional photochemical model, where we input surface fluxes and generate atmospheric mixing ratio profiles of the gases of interest. We then use those atmospheres as inputs into the spectral mapping and radiative transfer code, which allows us to generate transmission and emission spectra, which we'll particularly use at high resolution. And then we also use the planetary spectrum generator for spectral and instrumental modeling. And these 3 models enable us to do a fully vertically integrated observable, all the way from controlling the surface flux levels, looking at different stellar types, looking at different gases, all of that, to simulating a series of observables with synthetic noise and all of that. So before I talk about methyl bromide, we wanted to talk a little bit about methyl chloride. So methyl chloride was originally first described in 2005 using the Atmos model. And since then, there have been some significant changes made to the model, primarily in the form of updating the reaction rates and the photochemical cross sections that kind of are key to generating this data. And so as a result of these changes, the Atmos model no longer directly replicates the previously published results from Segura et al. 2005. Our version of the code specifically generates lower atmospheric mixing ratio profiles, but we do maintain the same overall conclusions. And I'll be using our version of Atmos and our code to benchmark the methyl bromide results in the rest of this talk. Speaking of which, here are some outputs from Atmos. So on the left side, you're seeing methyl chloride. On the right, methyl bromide. We're examining these 2 gases for a series of different surface flux conditions and stellar types. So the green line on both plots represents the globally averaged Earth's mixing ratio, and the blue line is showing 1 ppm for the atmospheric mixing ratio. And you'll notice that as we move towards later type stars, the atmospheric buildup increases pretty significantly, and this matches with what was previously reported from methyl chloride and what is expected for methane as well. And that is primarily because the main atmospheric sink for both of these gases is reaction with the hydroxyl radical, which is generated photochemically. And in these late type stars, the low NUV flux results in limited production of that radical, which allows higher levels of atmospheric buildup. One thing that you can note from the position of the green lines is that the globally averaged flux for methyl bromide is lower than that of methyl chloride, but they build up to within about an order of magnitude of each other, which actually indicates that methyl bromide has a greater relative atmospheric buildup than methyl chloride, which is kind of a unique advantage of this gas, which is particularly useful, especially because those fluxes are a little bit lower here on the Earth. So we use these outputs from the photochemical model as inputs for spectral simulations. What you're looking at right here is a grid of mid-infrared emission spectra, which are simulated for a future mission capable of that mid-infrared emission spectroscopy. Specifically, we're looking here at nearby small stars. So in the top row, you're seeing an atmosphere with methyl chloride added. In the middle row, you're seeing the addition of methyl bromide. And the bottom row shows an atmosphere with both gases added. And if we kind of go column, if you go column by column, you're comparing the results for each star. One large feature that really stands out, particularly for the M dwarfs in the top and bottom atmosphere, is the suppression of the 9.65 micron ozone band, which results in a really significant drop in that emission flux right around 9.65. And that is actually right next to where we see the methyl chloride and methyl bromide absorption features, which are a little bit easier to pick out in the methyl bromide row, which is the middle one. And so the methyl chloride and methyl bromide features are actually located right next to each other. And that results in kind of a larger feature that sort of is built from the two kind of connected to each other. And you can see that a little bit more clearly in this slide. So these are simulated observations using the Origin Space Telescope concept, which we use here as a blueprint for a future space-based telescope capable of imaging biosignatures in the mid-infrared, specifically one with a low noise floor at these wavelengths. So you could see here around 10 microns, the red line shows the methyl chloride flux, the blue line shows the methyl bromide flux, and again, this purple flux is showing an atmosphere with both gases. And you can see that this both gas atmospheric feature is larger than either of the two features kind of combined, and it results in this broader overall signal because these features are right next to each other. And that's actually not a coincidence. That results from the bond energies of methyl chloride and methyl bromide, which is directly related to their atomic structure and kind of their nature as both methylation products. You can notice here as well that drop in the ozone flux right around, again, 9.65 microns at the prominent ozone feature there as well. Additionally, there's also another feature right here around 7 microns where you can see, again, this atmosphere with both gases is producing a little bit more signal than either of the other two cases, which kind of matches with the results that I'm showing on the right-hand side of the slide here, which is this bar chart showing the number of transits that you would need to detect the methylated gas feature at either 6.9 microns or 10.2 microns. In both cases, the methyl bromide the methyl bromide feature requires more transits to detect than the methyl chloride feature, but the atmosphere with both gases is the optimal observation case for all of the cases that we considered here. And specifically at 10.2 microns for this productive methyl chloride and methyl bromide atmosphere, we think we can observe this in about 30 transits, accounting for the noise per transit and in and out of transit noise. So that is sort of the best scenario for observing methyl chloride and methyl bromide. So what this is showing right here is basically one way you could determine the existence of a methylated gas feature. And in combination with high-resolution ground-based spectroscopy, which is what I'm showing simulations of here, we believe that you could actually determine and characterize the specific methylated gas that is present because of the unique band structures of these gases. So we're looking at the same 4 atmospheres, the atmosphere with no methylated gases, with methyl chloride only, with methyl bromide only, and then with both gases. And you can see that these are not identical. And so we think at the high resolution that we expect to be possible using the extremely large telescope class, that we would be able to potentially uniquely characterize the specific methylated gas. And so that's a kind of a useful synergy between the ground and space-based telescopes that would enable us to first identify a methylated gas feature and then potentially determine the identity of that methylated gas feature using the 2 different observing methods. So one thing I really want to emphasize here is that we're talking about methyl bromide as what we're calling a capstone biosignature. And this is specifically because, these number of transits that I've shared are a little bit high. This is not something that we would necessarily be able to detect right away or using JWST. However, the methyl bromide has a very low abiotic potential, which sort of results in it potentially being used as a tool to differentiate false positive and true positive scenarios. And so, like I showed a few slides ago, methyl bromide can actually be detected alongside ozone features because they sit right next to each other in the mid-infrared, or potentially detection of a primary biosignature like oxygen or ozone that is a little bit more ambiguous. Could motivate intensive follow-up observations like what would be necessary to detect methyl bromide. And so methyl bromide is actually just the first in a kind of a series of methylated biosignatures that we're really interested in looking at. So the next steps from here are we're going to look at iodine species, specifically methyl iodine, which is kind of the third methyl halide that fits with methyl chloride and methyl bromide that I've already described. We're also interested in looking at what are called polyhalomethanes, which are these sort of more complex molecules where there's both a methyl group and potentially a bromine and a chlorine, or a chlorine and an iodine, or some kind of more complicated structure there. And that is specifically because here on the Earth, these polyhalomethanes have fluxes that are equivalent to or higher than these gases that we've already studied. So we kind of qualitatively expect that both adding the methyl iodine and these polyhalomethanes will improve the size of our methylated gas feature and decrease the number of transits necessary to detect a methylated gas feature. And a lot of these gases are produced by the same organisms or in the same local environment. So it's something where we would potentially expect to see many of these present under the same atmospheric or local environmental conditions. We're additionally interested in kind of expanding on the work that was done on dimethyl sulfide and expanding into looking at selenium and tellurium, which are kind of the elemental analogs at heavier weight for sulfide. And particularly looking at how those might also influence the spectrum of our methylated gas feature. Another component of this work that is not using the modeling pipeline is we hope to do laboratory and field measurements of the fluxes of these methylated gases, specifically to inform that model input, and specifically looking in local environments that are connected to the environmental detoxification process, and kind of thinking about where can we apply these gases on exoplanets realistically and have it kind of make sense and be appropriate for the rest of the context. So we do have a paper currently under review at AbJ, so hopefully that will be out sometime this summer, so definitely keep your eyes out for that. And with that, I'll leave you with my conclusions, and I'll be happy to take any questions that you have now, or you can shoot me an email. My email's on the slides, and I'd be happy to chat more over that way as well.
Hi, Michaela, Amber Young from Northern Arizona University. Awesome talk, really great work. I was just curious to know whether or not we might be able to detect methyl bromide in reflected light observations. So basically maybe 0.8 to 2 microns, if there's any absorption features in that wavelength range.
So as far as we've looked at, the absorption features don't really start until, for methyl bromide, I want to say like 4 microns or something like that. So it doesn't really seem like, at least right now, reflected light would be a good option for those unless we're able to identify some kind of shorter absorption feature.
Gotcha. Well, nonetheless, the transit features definitely look really deep. So it's exciting work, really cool. Thank you.
Thanks, Amber.
Hi, Michaela. Thank you for a really great talk. Just a couple of, Sukrit Ranjan, Northwestern University. I was wondering if you could comment on the stellar and planetary parameters kind of assumed in these simulations, as well as what the noise floor assumed was.
Yeah, so as for the specific noise floor, we use the Origin Space Telescope concept as modeled in PSG. So that's a question that I would have to get back to you on because I'm not familiar with the exact noise modeling specifics. And then for the planetary and stellar parameters, we use a series of different stellar spectra that are sort of input into Atmos and then the radiative transfer models as well. For the planetary parameters, we assume basically just an Earth-like atmosphere for start. And then for the case of Proxima Centauri and TRAPPIST, we're actually specifically considering the planetary parameters of Proxima Centauri b and TRAPPIST-1e. But for other than that, we're just sort of using a generic Earth-like atmosphere and Earth-sized planet to start with.
Got it. Thank you.
Hi, Michaela. Nick Wogan here from University of Washington in Seattle. I was wondering what concentrations of methyl bromide you would expect on the Archean Earth or an Archean Earth around an M star.
That's a great question, and probably something that I would have to think a little bit more about. We are planning to sort of expand into simulating these fluxes in anoxic atmospheres, and then also potentially doing some laboratory experiments to determine what these fluxes could be kind of under an anoxic or Archean-like atmosphere. So I don't know yet, but hopefully I can get back to you when we've looked into that a little bit more.
Cool, thanks.
Let's thank Michaela one more time. And then we have a talk from Jeff Fisher, who's going to walk us through some chemical reaction network topology. Jesse?
Hello, good morning to you all. So yes, cutting straight to the chase. So as I'm sure most of you are aware, the major challenge with studying exoplanet biosignatures is the difficulty that comes from going from a one-dimensional spectral plot to being able to confidently say that a biosphere is present on a planet. This is made increasingly difficult, in addition, by the fact that in the last couple of years, we've realized that a lot of gases that we normally associate with biological activity, like oxygen and methane, can also be generated through completely abiotic processes, raising the very real risk of false positives. And on top of that, if we may not even be able to accurately predict what biological gases may be relevant to biochemistries that are radically different from our own. So my goal for my dissertation has been trying to figure out how do we work around these problems. The approach we started with the idea that let's think about life as a pattern of interactions. After all, we usually do not find life in isolation here on the planet. It's usually in the context of an ecosystem, a pattern of behaviors and interactions with other life forms and its physical environment. Now, one good way to study how complex systems interact with each other is using networks. Essentially, you can take any complex system and represent it as a network by simply assigning each component of the network a point or node, and then connecting these nodes to each other via lines or edges that represent the interactions between these subcomponents. Classic example, and then from there you can mathematically analyze the shape and structure of the network, which will give you insight about the nature and behavior of the system you're looking at. Classic example is that the structure of the sort of crisscrossing of the US interstate highway system has a very different shape and topology from the hub and spoke system used by the airline industries, and that these can be mathematically quantified. So some of the network measurements we'll be talking about today are actually pretty straightforward. First one is degree, which in plain English is the number of connections or edges going into a given node. You can then zoom out and look at the entire network and take the mean degree, which, as the name suggests, is the average number of degrees of any given node in the network. Similarly speaking, the shortest path length, you guessed it, is the shortest distance between any two nodes in a network. And you can also take the average for this to learn more about the properties of the network as a whole. One last cool thing you can do with networks is to incorporate information you may have about the nature of the interactions into the edges of the network. For example, if this were an unweighted network and you wanted to know what the shortest path between points A and C is, it's pretty simple. You go from A to B to C. But let's take the weights and assume that they represent, for example, physical distance. In that case, the shortest distance between A and C is actually going from A to B to D to C, because that has a weighted shortest path of 5 versus going from A to B to C, which has a weighted shortest path of 6. So this can make network analysis a very powerful tool for understanding these sorts of complex systems. Now, you may be asking yourself, okay, that's great. How do we apply this to atmospheres? Well, you can do the exact same thing with any set of chemical reactions by assigning each species present a node and then connecting them to each other based off of what reactions they co-participate in. For example, with this very simple set of reactions, you can represent it as a network, then take measurements about it. The mean degree, for example, is 2.3, which in this case represents that each species, on average, is active in about 2.3 reactions. And the average shortest path length is 1.54, so each species is about 1.54 steps removed from any other species. Very handy. The reason we took this approach is because way back in 2004, two network theorists, Soleil and Montagneux, mostly out of curiosity more than anything else, decided to represent all the major planetary atmospheres in our solar systems and their chemistries as networks. And the vast majority of them ended up looking like this, sort of this jumbled mess of spaghetti. I believe this one is of Mars in particular. However, Earth looked like this, which is pretty noticeable. It has a structure to it that the other networks did not have. It is modular, it is hierarchical. And so this really got us wondering, maybe this is due to the presence of a biosphere. So, like I said, Soleil and Montagneux were network theorists. They weren't atmospheric chemists or planetary scientists or astronomers. They were mostly just doing it because they wanted to see what would happen, and that was about it. So we wanted to take their approach and do it in a much more chemically rigorous way. To sort of like do a proof of concept, we used hot Jupiters at first, because they're relatively simple compared to terrestrial planets. There are only a couple of major physical constraints like temperature and initial composition. And we actually have a paper that has been accepted at the Astronomical Journal about this research, if you're curious. And we discovered that the network topology does correlate to how far away you are removed from chemical equilibrium, in this case quantifying chemical equilibrium using the vertical mixing coefficient, or KZZ. So that was really encouraging. You know, we can actually tie network properties of chemical reaction networks to stuff that is actually happening physically in the chemical system we're modeling. There's also correlations with temperature as well, which is cool to see. Now you may be wondering what our pipeline was for this. Well, based off of observations, or in the case of terrestrial planets, which is what I'm about to get into, we take modeled atmospheres, or if we're dealing with hot Jupiters, the actual spectral lines, build a model, let it converge, extract the reaction list, and use that to build the network, and then weight the edges of the network using the calculated reaction rates generated by the model, and then measure the properties of those networks. And the end result is a distribution of network properties, because we were usually doing this with thousands of models, where, if you see in this last plot at the bottom center, each point in the curves represents the given network property of a modeled atmosphere and its corresponding network. So we now move to what we're really here for, which is looking at biosignatures, specifically, in this case, terrestrial planets and the Archean Earth. To better quantify how distinguishable these distributions of network properties are from each other, rather than just eyeballing it, we'll also use the Kolmogorov-Smirnov metric, which, real quick, is basically just a tool that tells you how statistically distinguishable two distributions are from each other. It gives you a value from 0 to 1. The higher it is, the more distinguishable. It also gives you a p-value, which tells you how statistically significant that 0 to 1 value is. So, you know, again, just a handy shortcut for quantifying how different these distributions are from each other. So, for our first batch, we modeled 10,000 terrestrial Archean Earth atmospheres with a Gaussian distribution of methane fluxes. Oh, that is the wrong figure on the left. Sorry about that. Oh, never mind. One of my slides got eaten. So anyways, just imagine in your head. The first set we did was a set of 10,000 planets, 5,000 that had a presence of a methanogenic biosphere. The other 5,000 just had abiotic methane fluxes. And it showed that the network measurements could distinguish between the two. However, the resulting methane fluxes for the biotic planets was also much, much higher than for the abiotic flux planets. So, you know, it's great to know that the network measurements, again, are representing something that is physically happening on a planet, but, you know, it would probably just be easier to look at the methane fluxes. However, we thought, okay, let's make this difficult for our would-be exoplanet astronomers. Let's assume we have planets that, for whatever reason, have the exact same amount of methane as the planets that have a biotic methane flux. For whatever reason, you know, maybe it just has a lot of methane left over from the primordial formation of the atmosphere. Maybe there's spectral contamination from an exomoon. Who knows? Some reason. And that's where our tool really shines. On the left, you have what the heck? Oh, whoops, I'm getting ahead of myself. That's why my slides are messed up. So, sneak peek. But anyways, this is just a demonstration of what I meant by two distributions. The one on the left is basically the same distribution, low KS value, high P value, not significant. The one on the right, two very different distributions, high KS value, low P value. So anyways, right, methanogens. First set we did, here we go. Like I said, biotic flux, abiotic flux. Methane concentration in the atmosphere is really high when you have life. It's much lower when you don't have life. not too surprising. Very high KS values for network measurement distributions as well, but again, you could just look at the methane flux. This is the tough case I was talking about. And as you can see here, knowing the methane flux doesn't actually really help you all that much. It yields a very low KS value and a very high p-value, so it's probably not that statistically distinguishable from each other. You would be hard-pressed to be able to tease apart these worlds, whether or not they have biology, just based off of the methane concentration in the atmosphere. However, if you look at the KS values for the network measurements, they're much higher. In some cases, almost double that of the KS value for the methane concentration alone. So this is really encouraging, and the p-values are also very low, so this is likely statistically significant. So that was really heartening to see that we can potentially be able to distinguish between these planets based off of network measurements, even when we wouldn't necessarily be able to tell based off of the methane concentration alone. What are our next steps, having proven that this potentially works? Well, first off, we want to do some applications of machine learning, which we also did for the Hot Jupiters project, essentially seeing if including these network measurements in training predictability algorithms makes it easier for those algorithms to be more accurate in predicting whether or not a given planet has life or not based off of the values we feed it. The other project that is currently ongoing as we speak is looking at abiotic O2 production and using some of the work from Harmon et al. 2015 and versus photosynthesis sort of in the early Proterozoic when the great oxidation event was just starting, because that's also a situation where you can have very similar levels of oxygen despite one planet being inhabited and the other planet not. And then finally, to actually see if we can use this for practical applications, an incoming grad student in my lab, Estelle Janin, is working on generating spectra from the atmospheres we've modeled using TAW-REX, and then seeing if there's any correlations between the spectral lines and the actual network properties, including some that we may not intuitively associate with each other, which I'm really excited to see. So yeah, there's going to be a lot of cool stuff coming up in the next year. And if you have any questions, and also if you're interested in what I'm doing, I'm going to be getting my PhD in the next 9 months, and I would love to have a job, so just let me know. But yeah, any questions?
Hi, Martha Grover from Georgia Tech. Nice to see you in person, Tessa.
Oh, thank you.
And thank you for the really interesting talk. Maybe you explained this, but I just wanted to make sure I understood or how about the p-values and the uncertainty. I would think from measuring concentrations directly and then fitting the kinetic model or the reaction model that there would be a lot of uncertainty. And is that uncertainty taken into account when you're distinguishing distributions? Or
yes.
Just interested to learn more about the uncertainty quantification.
Not for the set I showed, because these are literally just stuff that came out of our models last week. For the Hot Jupiters, though, we had a whole range of uncertainties in the initial physical conditions, and even, for example, temperature with uncertainties up to plus or minus 500 Kelvin, we were still able to distinguish using network measurements. I'm going to see if that's also true for these planets. I'm hoping it's the case.
Thank you.
Hello. I'll step a little bit away. Thank you for great talk. Very, very interesting work. I'm very, very interested in how you can distinguish between networks and network topologies, or whether your technique can distinguish between networks and network topologies that are complex but still achieve a sort of equilibrium versus something that's relatively simple but may not achieve an equilibrium, where the simplicity might come to our sort of ignorance. Like, I can kind of imagine throwing a bunch of carbon and nitrogen into a furnace and burning it up, and you can get a really complicated network.
That's actually exactly what happens with a lot of the hot Jupiter networks. That is actually another challenge we are planning on doing. Something I've been talking about recent with Sean Donegal-Goldman is looking at Titan, especially if you start factoring in ionization, you can get really high levels of complexity. We are hoping that the overall topology, if there's biology involved, is going to be different enough, but that is an open question.
Okay, thanks.
I think Sukrit will have to take the question during the break, so thank you. But one more round of applause for Tessa. And our next talk is from Thea Kazakis, who's going to talk about ozone as a proxy for molecular oxygen. Hello, come on up.
Do I just click forward here? Cool. All right, can everyone hear me okay? Great. Thank you all for coming, either because you intended to come or because you've become frozen into your seat and you can no longer leave. Also, sorry, I've been awkwardly standing out there because I was worried if I stayed in this room the whole time, I'd be chattering so hard you couldn't hear me. And shout out to the people standing out there. Thanks, Ravi. Anyway, so I'm Thea Kozakis. I'm a postdoc at the Technical University of Denmark. And today I'm going to talk to you all about a question that I'm really excited about, which is ozone, O3, a reliable proxy for molecular oxygen, O2? And geez, I am a little cold, so sorry if I'm chattering a little. All right, so you might have heard the joke that if a paper or talk title is a question, that the answer is no. And I'm happy to report that's not the case here. The answer is, it's complicated. So, ozone, the photochemical product of O2, they don't have a straightforward relationship. It's complicated. But I do believe that with the proper modeling, we can understand that relationship and work with it. So now that I've given you the really short answer, let me give you a bit of a longer answer. And we should start off with, why do we want to use ozone as a proxy for O2? A big part of this is that O2 paired with a reducing gas is a really promising biosignature pair. So we're going to want to look for these gases in the atmospheres of terrestrial exoplanets. However, there are scenarios where O2 is either very difficult to detect or not possible to detect. And in these scenarios, people have suggested using ozone, photochemical product of O2, as a proxy instead. So just to give a couple of examples of where ozone might be the better bet here. For example, you have the mid-infrared. So there's several missions proposed to look for biosignatures in the mid-infrared. And there are no significant O2 features. Yeah, life mission, Daniel, sorry. So there's no significant O2 features in the mid-infrared. So these missions will rely on ozone. Also, ozone is detectable at trace amounts, which means if you do have a planet with low O2, ozone might be the better bet there as well. So for instance, the Proterozoic Earth, after the Great Oxidation Event, we had oxygenic photosynthesis, but it took a while for O2 to build up to the relatively high levels we have today. So a planet like that, ozone might be the biosignature we want to look for. So let me tell you about how ozone is created. It's created through these reactions we call the Chapman mechanisms. And basically what happens is you have an O2 molecule and it's hit by a UV photon. The UV photon has to be less than 242 nanometers in order to break that strong double O2 bond. It then creates oxygen atoms, and those oxygen atoms can then recombine with molecular O2 with the help of a background molecule to carry away excess energy to create ozone. So note that this ozone formation reaction is a three-body reaction. Not to put in spoilers, but this is foreshadowing for 3 slides from now. Also, you might be looking at these reactions and thinking that the ozone-O2 relationship is straightforward. So I just want to put in the disclaimer right away that we've known that they have a nonlinear relationship for a really long time now. And that because of the UV dependence on ozone formation, the ozone-O2 relationship is going to change depending on the host star. And because of that, it's really important to do photochemistry modeling if you want to think about ozone. So that's what I did. So I used Atmos, which is a coupled 1D climate photochemistry code to model the atmospheres of terrestrial planets. And then I used Picasso, a radiative transfer code, to create planetary emission spectra for these model atmospheres to get an idea of what ozone emission features would look like. And for all of these planets, I used modern Earth initial conditions, but I changed the O2 abundance from 0.01 to 150% our present atmospheric level. And that's the PAL abbreviation you're going to see here a lot. And also for reference, our present atmospheric level of O2 is at 21% of our atmosphere right now. So let's start with the results for the Earth-Sun case. So here I have ozone on the y-axis, O2 on the x-axis, and then these vertical lines here just pointing out some cases of interest. So you have 100% the present atmospheric level of O2, so modern Earth, and then 10, 1, and 0.1%. And right away, you could see that I didn't lie. The relationship is complicated. There's sort of similar levels of ozone for both the modern Earth case and if you reduced Earth's oxygen content to only 10% of its present value. And peak ozone abundance occurs at about 25% our present atmospheric level of O2. So that might seem a bit strange, but fortunately, there's a relatively simple explanation for this. And it all boils down to the fact that when there's less O2, ozone's going to form in a deeper layer of the atmosphere. And I'll explain this by showing these two model atmospheres here. And they're both going to have the same background gases, and all I'm changing is O2. And one's going to be like modern Earth, and the other is going to be half of the O2 we have on modern Earth. So for modern Earth, here's our O2 molecules. And these arrows are representing UV photons coming in, breaking apart O2, and forming ozone. If we look at the comparison case with half the amount of O2, put in those arrows, you could see that just because there's less O2 in the atmosphere, the UV photons can get deeper, so ozone forms deeper in the atmosphere. And the reason why this matters is because ozone is created with a three-body reaction. And three-body reactions are faster if they're happening in a denser region of the atmosphere. So that's why when you decrease O2 levels at first from modern Earth levels, you do have more efficient ozone production. And for some O2 values, that sort of overcomes the fact that you're taking away the source O2 to form ozone. All right, let's look at the O2 ozone relationship for other types of stars, because there's a lot of stars in the universe, and we want to look for life around all of them. So here are the UV spectra of the hosts that I model planets around. If you are not an astronomer and you're not familiar with our interesting spectral type classifications, just know when you look at this legend, when you go from top to bottom, you're sort of going from the hotter stars with more UV down to cooler stars with less UV. It's just a simple thing. So let's look again at this ozone O2 diagram. There is the sun, which we looked at the last slide. Now I'm going to add on the G0 star and the K2 star. So those are the two other hottest hosts that I looked at. And just looking at them quickly, you could see the ozone abundance is different for them, but they follow sort of that same trend there. Because when there's less O2, ozone forms deeper in the atmosphere. It's more efficient. But let's look at the two coolest host stars I looked at. So we have a K5 and an M5. And right away, you could see that those are different relationships. Those are different trends. And if you take away O2 in these cases, you always get a decrease in ozone. And the reason for this is just that there's less UV light reaching these planets. So if we return again to this diagram that I showed a couple of slides earlier, if you want to look at a planet with less UV, we can sort of approximate that by just deleting a couple of arrows. And you could see that basically the UV light doesn't get that deep in those atmospheres, so the ozone layer doesn't move down as much as the hotter stars. So you don't have that really efficient ozone production. And that's why if we return to this diagram again, the trends are different depending on the host star. So again, photochemistry modeling is going to be really important if we want to use ozone as a proxy for O2. And I also want to show you some of the emission features that I simulated for these models. So here for Earth around the sun, here's the 9.6 micron ozone feature. And right now I'm showing it for the 0.1% present atmospheric level of O2 case. And let's increase the O2, see what happens. So here's 1% our present level. That feature's deeper, that makes sense. 10%, that's sort of overlapping with the 1% case, which is interesting because there's significantly more ozone in the 10% case than the 1% case. And 100%, which is shallower than both of those, which seems interesting. It's a little complicated, but we can understand this. And the reason is that the depth of emission features is dependent on the temperature difference between the emitting and absorbing layers of the atmosphere. So for ozone, that's going to be the temperature difference between the planetary surface and the stratosphere where the ozone layer exists. So here are the temperature profiles of these cases. And if you look at the black line, the modern Earth case, you can see there's a huge temperature inversion there. And that's because most of the stratospheric heating on Earth is through UV absorption of ozone. So even though this case has a lot of ozone, as a result, the temperature difference between the surface of the planet and the stratosphere is much less than, say, the 1% case where there's significantly less ozone, but the temperature difference there between the surface and the stratosphere is much greater because it doesn't have the ozone stratospheric heating. So climate modeling is going to be really important too for using ozone as a biosignature. And last, I just want to show you these corresponding emission features around an M dwarf. So that's the coolest star that we looked at. So here is, again, the 0.1% present atmospheric level of O2, 1%, 10%, 100%. That might have been a little underwhelming. Thank you, Eddie. So these features are a little more, in a way, straightforward to what you might have intuitively guessed. And if you look at the temperature profiles, you can see why. You could see that none of these cases have the stratospheric inversion. And that's because, first of all, there's less ozone in these cases, but also because there's less UV reaching the atmospheres of these planets for ozone to absorb. And it's through that UV absorption of ozone that the stratosphere is heated. So in a way, around cooler stars without temperature inversions in the atmosphere, in a way that gives a simpler emission feature. But again, climate modeling is going to be really important here. All right, so I've just thrown a lot of information at you, and I hope that you can agree that the relationship between O2 and ozone is complicated, but that if we do the proper modeling, we could start to work it out. So we're going to really have to understand the UV spectrum of the host star and do the atmospheric modeling. So if you're interested in this project, please feel free to pull me aside to chat. You can email me. You could message my Twitter. It's just my name. Or you could ask me a question right now in this Q&A session. Thank you. I think Sean won.
Hey, Sean Domingo Goldman, NASA Goddard Space Flight Center. Two questions maybe if there's no others. The first is, did you look at the ultraviolet absorption feature as well as the 9.6 micron feature?
Sorry, I missed the first part. Did you ask if I looked at the UV features? Yep. So not in this current paper, but I am very interested in it, especially since the future great observatories, so this LUVEX, or as I call it, baby LUVOIR thing, I know that they specifically want their wavelength range to include the UV ozone absorption in the hopes that you could use ozone to find low levels of O2. So I haven't looked at that yet, but that's a future plan because I'm very interested in that feature as well.
Yeah, we'd be super interested in that.
Yeah.
The second question, if it's okay. I'm actually thinking about Stephanie's work, the woman to your left, and looking at the seasonality of oxygen fluxes.
It's a good paper.
Yeah, and combining that with like what you're doing, which is like looking at the different star types. Have you thought about that? Like, are there plans for that? Because I think that would also be just fascinating to see.
Yeah, so I forgot to mention, sorry, I keep hitting the microphone because I'm wearing a mask. So I forgot to mention, this is going to be a series of papers, and the seasonality is something I'm really important in, because obviously that's going to change the ozone abundance and, day-night cycles, tidally locked planets. It's going to change for everything. So these are definitely things on the to-do list that I'm really interested in.
Cool. Looking forward to all of it.
All right. Thanks so much, Sean.
We have time for maybe one more quick question, and if no one else is going to ask it, I am. So, no? Oh, please.
Hi, I'm Angela Burke from Purdue University.
Hi.
I was wondering if you had plans to study non-Earth-like exoplanets?
Yeah, that's a good question. So right now, so there's so many questions I have for the Earth-like exoplanets right now. Like I'm working on things where I'm changing like methane abundance and nitrous oxide abundance because that changes ozone, and then like working on different boundary conditions in the models change it. So right now on my to-do list, it is only Earth-like planets, but of course this is going to be important in all types of planets. So I'm not currently planning on it, but I think it's important. If that's something you want to do, you should totally do it.
Thank you.
Or if that's something someone else wants to do, I think it's important. Maybe once I get through all the Earth-like questions. Yeah.
Let's thank Thea one more time.
Thank you.
And next up, we have Ryan Felton, who's going to talk to us about the role of atmospheric exchange in false positive biosignatures.
Okay, good morning, everyone. I'm Ryan Felton. I'm NPP out at NASA Ames in beautiful sunny California. And along with my co-authors listed here, I wanted to talk to you about a paper we recently published titled The Role of Atmospheric Exchange in False Positive Biosignature Detection. So this work was all first inspired by thinking about the Titan Enceladus system, where essentially you have the cryovolcanoes on Enceladus that are spewing out organic volatiles that are then entering the Saturnian system, cycling through it, and some of it actually becoming incorporated into Titan's atmosphere. And so we thought, well, could a similar type of interaction occur amongst exoplanets? And so we envisioned this hypothetical here, where in the TRAPPIST-1 system, you have TRAPPIST-1d losing its atmosphere due to extreme stellar activity, and that material blowing off from TRAPPIST-1d, moving out into space, and essentially raining down onto TRAPPIST-1e. So we thought, well, if you have all of this extra material entering into another atmosphere, could you trigger some kind of false positive biosignature now that all that extra material is there? And so the biosignature we wanted to look at is one that's a historically strong one. It's just considered the methane and O2 or O3 biosignature, where essentially you should not really see both of these at the same time due to the way that they interact, where either in an abundant oxygen environment, the methane is going to be destroyed, or in an abundant methane environment, the O2 will rapidly be lost to reducing sinks. So the only time that you should see the two of these at the same time is really if there's something else that's replenishing it. And our understanding is that that mechanism would need to be biology. And so again, could an external material influx amongst exoplanets cause a false positive? And to begin answering that question, we turn to the TRAPPIST-1 system, specifically TRAPPIST-1e. We took an Archean Earth simulation and started essentially making it a TRAPPIST-1e1 using the 1D photochemical climate model, ATMOS. And we applied Archean Earth surface pressure, but then essentially everything else was TRAPPIST-1e based, so the planetary parameters and stellar installation for that system and planet. And we needed to bound the problem. So to begin, we had methane surface fluxes. This is just methane coming out of the surface. And we binded based on these three categories here, either abiotic, ambiguous, or biotic. And these bindings are essentially just based on literature and how we've been breaking these down. And then we wanted to have two fluxes. So this is the material that's coming into the external material coming into the top of the atmosphere. So the first one is oxygen. And we set lower and upper bounds. So the lower limits are really just based on Titan research and Cassini-Huygens results. And the upper limit is based on simulations of Proxima Centauri, where it's essentially due to stellar activity is having ionized atomic oxygen stripped off of it, and the flux or the molecules per centimeter squared per second for that was on this range of about 10 to the 10. And then another flux that we wanted to incorporate here to test this was water. So now you can just think of a water hose, this spigot, you turn it on, and it's spewing water out onto the top of the atmosphere. And again, we turned to Titan to establish a lower limit for that flux. And the upper limit is really based on kind of just a back of the envelope calculation for water loss on Earth, and then converting that to the appropriate flux. And so first, I just want to show you some of our photochemical results. What you see here is methane and ozone column density on the y-axis as a function of the incoming water flux. And then the boundaries that I discussed are, you can see here in orange and black, are the vertical dashed lines on the left and right. And then the region to the far right, past that black line, is essentially what we consider the physically implausible region. So these are not fluxes that really should be occurring in nature. And the big takeaway here is you can see that as you're moving from left to right, as you're turning up the dial on the amount of water coming out, the atmosphere is gradually starting to respond to that. And the same thing now just with oxygen. Again, we have our limits on the left and right, and then that in physically implausible region on the far right. And so with our simulations, our photochemical simulations in place, we needed to next turn to actual observations. What could we see? And to do that, we turned to planetary spectral generator, or PSG. We also incorporated water and water ice clouds. So we weren't just painting on an albedo, we could actually have a little bit of more realism applied to it. And within PSG, we had 4 telescopes, 5 instruments. And James Webb, of course, because it's now launched, and it was actually, it was interesting. We were between, when we started this, it had not launched, and then while we were in review, it launched. And then the other telescopes are based on the Astro 2020 decadal mission concepts, HabEx, Origins, and LUVOIR. And so let's get to some of the results here this is for the PSG results. And so these are signal to noise ratios versus observatories. And we were looking for a minimum of 5 sigma or 5 SNR as considered to be a reliable signal. And so what we have here is when we're looking for methane signals. So remember, there's at least 2, where we're looking for 2 to 3 biosignatures or 2 to 3 gases. And so you see here that the only telescopes that have any SNRs for the methane for when oxygen is flowing into the top of the atmosphere are Origins and LUVOIR. And then the color codes here break down by what you can see on the far right. So blue is 5, yellow is 10, and gray is 20. And that's really just based on the fact that James Webb had such a successful launch, and so it's estimated that it will have a 20-year lifetime. So we extended the mission lifetimes and in turn the transits for all of our telescope simulations. And one thing to note that was interesting, we did apply a 10 ppm estimated noise floor for James Webb. And you can see here that for near spec prism, we actually hit the noise floor essentially immediately. And so any further transits did not increase the SNR. And this is for cloudy. And then for clear sky, I'll just put these together. And so the solid is the cloudy, clear is the dashed diagonal. And as you would imagine, in a clear sky, the observations the SNR is going to be improved. And then an example of one of our strongest methane signals, and I say strongest here even though it's cloudy just because that would also potentially be the more realistic, was for LUVOIR. You can see the sigma here of well over 5 sigma. And the feature we're looking at is the one at 2.33 microns with the vertical dashed line on the far right. And the other features are really just highlighted to kind of show you what else is out there and also just how heavily blended these spectra can be. Even though you do see things there where there is another methane, there's CO2, they're also blended with other gases. And the ability to break them out may not be, it's going to be harder than you would imagine. And so that's what you can see here in the transmittance, where the overlay of the other gas is based on the percent that they're blocking. And so now that was one guess, though. And remember, we're looking at the methane and O2, O3 biosignature combination and trying to see that. And so I'll tell you, no, you actually do not find O2 or O3 at any appreciable SNR levels for the boundaries that we established within this project. And those boundaries, again, are all based on either stellar activity or tie-in, essentially physical limits that we already have understandings for. And so all of these SNRs were either less than 1 or they were or for LUVOIR, I believe there was 1 oxygen signal, but it was so heavily covered up by the noise, which is well over 500 ppm, that you were just never going to actually be able to resolve this. So this is good. This actually tells us that when we're looking at the TRAPPIST-1 system with the upcoming James Webb cycles, the guaranteed and general cycles, we should not be worrying about coming across this potential false positive. Now, I also wondered, though, okay, well, how much do we actually push this to see something? And you do have to push it past the physical bounds. That's what we see here. So if you look at the bottom right, or sorry, at the bottom middle, the water and oxygen TOA are top of the atmosphere flux. They're 10 to the 12. So this is now 2 orders of magnitude above the limit that we impose, and so essentially 2 orders of magnitude outside of a realistic scenario. And Origins is the only one that shows a SNR, a simulated SNR of 5 or higher, and it's only in the 20-year lifetime. But this is, again, within an implausibly physical region. And so to conclude, as I was saying, we do not need to be concerned about this false positive for at least the TRAPPIST-1 system, especially for M dwarfs. You really need to be at least 2 orders of magnitude above what would be physically plausible. And no, we will say that we did not consider other potential biosignature combinations like methane and CO2. And there's no space observations, or sorry, we only did space observatories, so there's no ground base to look at yet. And if you're interested in any potential collaboration, just come say hi. Any questions?
That was a very nice talk. Thank you very much. Katia Macheva from University of Florida. You were quoting as an example, as an analog for the work, the interaction, possible interaction between Titan and Enceladus. Those analogs are very far in the solar system. They're kind of in a regime where the radiation from the sun is not strong enough to destroy those molecules in the interplanetary distance. How about in a condition for the TRAPPIST-1? Those are very close to the hosting star. How do you model the survivability? How these molecules survive outside the host planet?
Yeah, so we thought about this. Essentially, we took this stoichiometric argument that anything that would be broken up, we essentially applied a 1-to-1 ratio. So anything that would get out of the atmosphere would be blown off at that first planet, like TRAPPIST-1D in our in the picture. We just we went with the stoichiometric argument that anything that was left and broken up would come back together in some way when it entered. At least that was the best way to move forward with it.
All right, if there are no more questions, another round of applause for Ryan. And at this time, hand it over to Stephanie, and I'm going to step.
All right, our final talk of the session comes from Felipe Gomez, who will be talking to us about photosynthesis on exoplanets.
Hi, hello, can you hear me?
We can hear
Hello?
you, but we can't see your slides yet.
Okay, I'm going to share because we have some problems. Yeah, right now I'm trying to get into my presentation, which is right here. Can you see the slides right now?
We can see them now.
Okay, thank you. This is Felipe Gomez from the Centro of Astrobiology, Astrobiology Center in Madrid, in Spain. And I am presenting our work, photosynthetic activity thickness in exoplanetary systems. This work is an attempt to know how the origin of photosynthesis could be on our planet, and by extrapolation, if it could be possible that this kind of photosystems, like the ones that we have on planet Earth, could work in other solar systems. In this abstract, we would present not only the evolution of the first probably photopigments on Earth, if not the real fitness of this theoretical photopigments photopigments, and at the same time, the regular ones that we have on Earth right now. Since the very beginning of the human being, the different cultures can observe the sky, and many questions have been asked. Are we alone in the universe? Are there other Earths with possibilities of life? Philosophers, artists, scientists have contributed from their point of view to the advancement of this knowledge. And of course, the question about how could they resemble other planetary bodies in the case of any kind of photosynthesis would take place. With the technology, the technology that we have nowadays, the drop of water of knowledge in the immeasurable ocean of ignorance could be a little bigger, bringing light to the great darkness that has surrounded these issues in the past. 50 years ago, the Voyager, this slide show, the Voyager probe took a picture of Earth that Carl Sagan called the pale blue dot. If this probe had carried a spectrometer on board, it would have identified a discontinuity between red and infrared. It is what we know as the age in red, and is due to the vegetation on Earth. Responsibly is photosynthesis, the process by which plants obtain energy and nutrients from CO2 in the atmosphere, water, and sunlight. Photosynthetic pigments such as chlorophylls and bacteriochlorophylls, which are the basis of this process, absorb blue and red wavelengths, which is what makes vegetation green. The range of the spectrum that we identify in green is the part of the radiation that plants reflect because it's not used in the photosynthetic processes. So now we ask ourselves again the question that our ancestors already asked themselves: would photosynthesis be possible on other planets? What kind of atmosphere would be necessary? And what distance between the planet in question and the corresponding star would there be? And not only that, what color, for example, a very simple question, what color could have the plants in another planet? To address this issue, we have created a group of scientists at the Astrobiology Center in Madrid, made up of chemists, astrophysics, biologists, electronic technicians belonging to the different departments, astrophysics, planetology and habitability at CAP. But this work is limited to certain types of stars, atmospheres, and photosystems. That is, we limit the three main parameters, considering them under the Darwinian principle of evolution. And that determine that possibility. Only those photosystems whose spectra overlap the radiation spectrum of the corresponding star will survive, taking into account the filter that the corresponding atmosphere is supposed to allow only that spectrum range that will be photosynthetically active to reach the surface of the planet. But in this study, we are going to go a little further. And we are not only going to consider the photopigments currently functioning in nature, such as chlorophylls and bacteriochlorophylls, but we are also going to use computational chemistry software to design theoretical pigments that could have been the origin of the current ones. Now, to do this, we will follow the principles of simplicity and thermodynamic advantage that allow us to guess which could be those first pigments that, after evolving, gave rise to those currently used by photosynthetic organisms. And why do we not consider photosynthetic organisms as such? Mainly due to the complexity of the photosynthetic systems. If it would already be difficult to deduce the origin and thermodynamic evolution of these protein complexes associated with pigments on planet Earth, you can imagine applying these theories to exoplanets. And at the same time, are those pigments which are finally absorbing the light radiation to run photosynthesis. This is the reason why we consider only the photopigments included in the photosynthesis processes. On the other hand, we have the second parameter, the atmosphere factor. There are different types of atmospheres, from oxidizing to highly reducing atmospheres. These atmospheres function as filters of solar radiation. allowing only a fraction of the total radioactivity of the star to reach the surface of the planet in question. We have calculated the transmittance using the free NASA Planetary Spectrum Generator software. Finally, we have to have in mind to consider only rocky planets located in the habitable zone of stars between types A and L that will be neither very cold nor very hot, and we have calculated their spectrum in the habitable zone with the BOSA tool that we have at CAP. We have crossed all these parameters, taking into account those pigments whose spectra overlap the stellar radiation that reaches the surface of the planet, and we have quantified this overlap with a metric that we have called a spectral absorption rate, that quantifies the number of absorbed photons per molecule and that yields an amount of energy. And this is the three parameters that can be possible to see in the slide right now. But let's see how it works with an example. If we combine the emission spectrum of the sun, on the top left of the image, with the transmittance of the Earth's atmosphere and the absorption spectrum of chlorophyll A on the right, we obtain its spectrum absorption rate, from which we can extract a lot of information. But what makes us different from other previous studies? In our case, we will follow an incremental and iterative life cycle in which we will add more and more types of stars, binary systems, types of atmospheres, and photosynthetic pigments. In the long term, we will use different convections using big data platforms, and we will also develop the Earth technical capabilities that allow us to iterate these results to design the corresponding search of exoplanets in the near future missions to detect this type of systems, all based on our own calculations. But we won't have to wait that long. We already have results. We have proposed a possible route of chemical and thermodynamically favorable molecular evolution towards the appearance of more complex pigments and evolved through cycle adding reactions whose intermediates can function as pigments, at least from a photophysical point of view. In the slide you already have right now these adding life cycles and the thermodynamically favorable reactions in which from the very top left, in which the precursors we think in the atmosphere in water cycle can finally render a molecule of FOT0. FOT0 is the previous origin of what we thought is the precursor of our actual photopigments in photosynthesis on Earth. It has also been simulated what happens to the photosynthetic capacity of different photopigments if we take our Earth as the beginning using different temperatures, but always placed at a distance from the star, our sun, in which liquid water of the surface of the Earth is possible planet, and we have found interesting results. Now you can see, for example, the photosynthetic capacity in stars between types A and G would be similar if the atmosphere of the planet absorbed an excess of UV radiation from type A stars, or that, for example, just on the right, bacteriochlorophyll B is capable of developing its function in a planetary system in the environment of an M-type star. ExoFOT has clear idea and development behind it. Perhaps it's a romantic idea that is taking us to the extent of the scientific spirit, because who of us present here now has not imagined what other worlds could be like. It is an ambitious but realistic project situated in that could be a new era of astrobiology. In that context of the ExoFOT project, we want to go further. We want to participate in this new era of exoplanetary research and establish a new line of research that allow us to know the real possibilities of systems that could host some form of metabolism based on use of the radiation coming from the star. But this work has stabilized a multidisciplinary team that allow us to have unnecessary research for it. That's all. Thank you. And of course, collaborations are welcome if anybody is interested on.
Any questions for Felipe?
Felipe, Eric Mamajek, JPL. What did you assume for the absorption by the planetary atmosphere? You showed the stellar SCDs, you showed the chlorophyll absorption, but they must be incredibly different photochemistries, and there could be a bewildering array of different planetary atmosphere compositions. So what did you assume for the absorption?
Yeah, okay, thank you for your question. I assume for absorption, the filtering process of the atmosphere. This means if an atmosphere with different chemistries, of course, and we have taken into account the different chemistry that could be run in these conditions, the atmosphere filter, for example, in our case on Earth, the sun radiation. This means that only a very small part of the radiation of the total atmosphere reach the surface of the planet. This is what we consider to filter, to reach the surface. Of course, at the second step, we consider as well any kind of possible reaction that could take place.
Any other questions? All right, let's speak Felipe and all of our speakers again.
Thank you.
That concludes our session for this morning. We will reconvene after lunch, but we will not be in this room. We will be upstairs on the 3rd floor. And then we have posters this afternoon. So looking forward to seeing you all later.